Okay, so this question, or this type of question, is getting back at the fundamental theorem of calculus and really kind of the proof of that fundamental theorem of calculus. And so what you're given sometimes is a graph, and it could look kind of all sorts of different ways. Maybe this one looks like this. Minus 1, 1. Something like this. Okay. And so we define g of x, and it depends a little bit how it's defined. We usually just start with some starting value. Here maybe I'll start with minus 1 to x of f of t dt. And what this question is trying to make you do is get a better understanding of this function, right? This accumulation function. And what you said is exactly right, that the derivative of that function is exactly f evaluated at x, right? So x, could be anywhere in this interval. The derivative of this function is exactly equal to f of x. So another way of looking at this is the derivative, right, of g. And we've done problems like this in the past where I give you the graph of the derivative, or ask you to sketch the graph of the derivative, or we use the derivative to tell us information about the function. So that's probably the most direct approach, well, the most calculus-like approach, I guess, right, is to understand that this function here, which is, we call it f of t, but you can also think of it as f of x. It's really okay. You just want to not confuse. I know I've talked about this a couple times, right? But it's like a kind of a formality to switch the t's and the x's. It is important here, g prime of x has to be equal to f of x, because that's like a point and it needs to match this point. But otherwise, we just don't want to confuse everything. So don't get confused that this function is labeled f of t. You can think of it as the same as really f of x is going to look the same here for this purpose. So for instance, if I want to know where g of x is increasing, if that's my question, well, then we know it's increasing when g prime of x is bigger than 0, right? When the derivative is positive, the function is increasing. But of course, the derivative is exactly f of x. So looking at our function here, I can see that the f of x is positive over this interval, right? It's above the x-axis here. And so g prime of x then is positive, which means g of x is increasing. So that would be on the interval from minus 1 to 1. You can also approach this problem by not thinking so much about the fact of the derivative and the function, but really just thinking about what g of x is. G of x is the area from minus 1 out to x, right, wherever x falls. And so we know from area that as long as x is in here, the function is getting bigger and bigger because I'm gathering more and more area. But as soon as x hits and moves past 1, all of a sudden now I'm gathering the negative area. So my total value for g of x is going to be getting smaller after 1. And it's going to be getting smaller all the way through here, because at every juncture I'm adding more negative area. So you could also answer the question that way. G of x is increasing from minus 1 to 1 because after 1, g of x is getting smaller because it's of the sign of the area that it's adding. So you can, those two pieces of information are going to match up, but they're different ways of looking at that accumulation function. sometimes thinking about it in area can be a little hard to visualize, perhaps, but that's also true with the derivative sometimes. But we do have more experience with the derivative, but it's a similar similar kind of argument. Let me go back to the question here and see, did that. Yeah, so I think, you know, with that question, you're gonna bounce back and a little bit back and forth between thinking about it as area. So one way is to think about this as area, and the second way is to think about it as a function that you know the derivative of. So if it asks you questions about the derivative of g, then certainly I'd like to use this. If it's asking me about the values of g, then I probably need to use the area definition. And, you know, on this graph in the take-home quiz, I think, and other graphs too, if I asked you for, say, g of 1, that would be all of this area. I would have to guesstimate that, right? I'd try and say, well, is that to me looks like about 2 roughly. Maybe it's a little less than 2, but you know, we're only able to estimate that value when we have a curve like that. Okay, does that help with your question?
Yes.
Okay, it's a good question. I personally think it's an important problem because you can't really understand the fundamental theorem unless you can understand what this accumulation function does and means. And that just takes a little bit of time and experience to kind of get a little bit of comfort with it. So that's really what this question is about. Other questions?
Yeah, I have a homework question.
Yeah, great.
Number 13, the one that says an integral from 0 to 16 x over the square root of 16 plus 3x.
Okay, is that from 5.5?
Yeah, 5.5 is the most recent one.
Okay. Let me just look it up. I know you said it, but I'll 13, was that?
Yeah.
Okay. So, sorry, what was your version? 0 to?
0 to 16.
Square root of?
16 plus 3x.
Okay. So there's different versions, right? Some of these numbers change.
Yeah.
And so our goal here, or instructions, are to evaluate. And as with the first question, this is a definite integral, just between two numbers. So I just need to, it's a value, right? I'm looking for the value of this thing. And as I talked about before, I'll repeat it again because I think it's important, right? We have the definition, which involves the sigma notation and the limit. We don't want to engage that here or really anytime because that's a ton of work, right? Even for simple functions. So we keep that and we understand that, but we certainly don't use that unless we are forced to, right, by myself. The second option is geometry, but again, that's for very limited functions. And in no way is this a function that I know what it looks like enough to use geometry. So without it being stated in any other way, we would definitely want to try the fundamental theorem of calculus, part 2, because that's what does the definite integrals. And so really all that boils down to is finding the antiderivative, right? If we can find the antiderivative, then the fundamental theorem tells us what this is. There is one condition which says the function has to be continuous on this interval 0 to 16. So if the function is not continuous, then the fundamental theorem does not apply. So we don't, and when I say we, I mean like the book and most ordinary teachers don't try and trip you up with that, because I think we know it's enough work just trying to get your head around these antiderivatives without having to think about that. But it's possible you'll see some problems where you're sort of warned, like, okay, something weird is going on here. Why is this not working, for instance? And in that case, you might then think, okay, well, the function has to be continuous, and then maybe that is what's causing things to go wrong, right? So this function is continuous from 0 to 16. There's no issues that make the bottom 0. So we're all good. And you don't have to normally check that, right? You can move right in here to the fundamental theorem of calculus, which means finding an antiderivative. Now we have to sort of, you wouldn't have to go through all that, like, flow chart. You would just jump right to the fundamental theorem of calculus. And in doing that, then we would think, okay, remember our rules here for antiderivatives. Is there anything whose derivative is this? No. Is there any way to simplify this using algebra? No, not with the square root part there. So my only other option is we've got to use substitution. And of course, you also know that because it's in 5.5, right? But that's not going to be the case on the exam so much, right? You'll have to think a little bit sometimes what you should use. So substitution. Sorry, I'm backing my way into your question, but it's good for everybody and myself. So when I look at this problem with substitution, I see a couple things. So like I do a lot of these. Well, over my life, I've done many of these. So I have to sort of stop and think, like, what are the things I'm scanning through? So when I look at this, I'm looking for a u, and then whatever that u is, its derivative is du. And I'm looking for kind of a relationship within the parts of this problem, where if I pick something as a u, then its derivative should also somehow be in the problem, okay? And so for instance, we also talked about last week that you don't want to pick something like too big for u. So an example here it's not crazy, but if you pick this whole bottom to be u, when you take the derivative of a square root, you get 1 over the square root plus like the chain rule. So the du then would be quite, well, somewhat complicated and is nowhere present in this problem. So my first thought is to say, okay, that's too big. That's too much. So the next kind of obvious choice would be this. That's the inside of the square root, and we know that kind of relationship with inside and outside is what the substitution rule is for. So 16 plus 3x, and then I take the derivative of this, which gives me 3 dx. Okay. There's no 3 here, but that's actually not a problem. I can put a 3 in and a 1/3 on the outside. Those constants can move in and out of definite or indefinite intervals. So I'm really just down to one kind of problem here, which is this x, this extra x in the problem. And so this is I'm glad you asked, because this is a problem that needs a slightly more sophisticated approach, or a little extra. In this case, I can't just eliminate or ignore that x. When I make the substitution, all the x's have to go to u's, and I can't have any x's left over, right? That doesn't work. Okay. It has to sort of all flip over to make that substitution happen. So what I notice here is that I don't know what x is exactly, but I could find it from this. Let's just rearrange this. It's just an inequality. So if I subtract 16 and divide by 3, I get that x equals u minus 16 divided by 3. So it turns out we're used to substituting like a function of x into a u, but you can also substitute x into a function of u as well. So this is all fine, all these substitutions, and this is going to allow me to replace x with u. Now, what's going to happen here is maybe still a little bit unclear, but let's give it a try. The x is going to become u minus 16 over 3. The square root of 16 minus 3x becomes the square root of u. And the 3dx becomes du. So let's do a little simplifying here. This 1/3 can come out and make a 1/9. So you may look at that and think, wow, okay, I did all this work. I don't know that this really looks any better, but it actually does. This is really nice. Well, better, let's say, because the denominator is now just a single term. It's a square root, but it's just a single term. So I can divide that into both of these. And that's going to give me 1/9. U divided by the square root of u is going to be square root of u. And then this is going to be 16u to the minus 1/2 du. I know I could have written that as u to the 1/2 of that, but I know the derivative of the square root, so I just kept that one as a square root. So the antiderivative and therefore the derivative. I don't know, maybe it's easier to write that one as u to the 1/2 too. Be consistent. All right, so this actually is good. I know these antiderivatives, they're power rules. I add 1 and divide by 3/2. And here I add 1, right, and divide by 1/2. Questions so far?
Wouldn't you have to change the bounds too?
So yes, that's a good question. I was kind of, you noticed, right, that I kind of waited on that as mostly just not to confuse you. But maybe that didn't work, right? So the question there is that the bounds, right, in my initial problem were from 0 to 16. Okay. Those are x values, 0 to 16. When you rewrite your integral into u values, you have two options. The best option is to just change these x values here into their corresponding u values. It turns out that that will give you the same value for the definite integral. So, and that's what I would do, and I would encourage you to do that as well. So here, when x equals 0, I just plug it into my formula. When x equals 0, u has to be 16. And when x equals 16, I plug that in. 16 times 3, 48, plus 16 is 64. Okay. So really at this point, like, all the calculus is done, but there is still some algebra and plugging things in that needs to be done, and it's a common spot to kind of get most of the way and then mess it up, right? So let's be extra careful here. When you're dividing, I would probably go ahead and distribute the 1/9, but you could save that to the end too. If you distribute it, this is going to be the reciprocal, so I get 2/27 times u to the 3/2 minus, that's going to be 32 over 9 u to the 1/2. So I plug in 64. And then I subtract the same thing when I plug in 16. And, you know, my preference is just to write everything out. I feel like that's safer. You could certainly do some of the simplification as you wrote it out, but I don't know. Always seems a little dangerous to me. So the square root, right, of 64 is 8. So this is 2/27 times 8 cubed minus 32 over 9 times 8 minus square root of 16 is 4. So that's 2 times 4 cubed over 27 minus 32 times 4 over 9. So, you know, you could figure this out with a calculator. I can make it look a little better by noticing 8 cubed is really 4 cubed times 2 cubed. So I have 8 of these, 2 4 cubed over 27 minus 1 of those. So I'm going to get 7 times 2 times 4 cubed over 27. And then I have minus 32, minus 8 32s plus 4 of these 32s is going to be minus 4 32s over 9. I'm just doing this in my head just because I only have my calculator right here, right? And this is, you know, if I were to give you this problem, I'd be overjoyed, right, if you just got to hear. So this is the part that I'm like not super interested in because it's kind of, well, it's boring, right? And easy to make little mistakes that are, you know, not great. So if you're doing a problem like this, just make sure, you know, especially on the test or something, just make sure you show me your steps, right? If I can see like, okay, you got the right antiderivative, you put in the right values, and then something went wrong between there and there, it's going to be like a really small deduction, like a half a point or something, right? I'm not going to be that concerned about that. I want to see that you can get to these stages. The other option, what you can do is you can replace the u values with the original expression (16 plus 3x). Okay, so there I replace the u's with the 16 plus 3x. If I do that, then my bounds cannot be the u values. My bounds have to be the original x values. Here, 0 to 16. This way is a little bit more work, I think. You're going to end up doing the same stuff in the end, and you're going to get the same answer in the end. And you can see it really quickly, right? Because if you put in 16 here, well, you get 3 times 16, 48 plus 16, you get 64. That's exactly what we got when we put in 64 directly, right? And then when you put in 0, you get 16, and that's exactly what we got when we put in 16 here directly. So it's really not important which method you use, but you cannot mix them. If you leave it with u values, that's fine, but don't take it from 0 to 16. those are X values, right? And if for some reason you decide you want to go back to the X values, that's fine, but then don't even mess with the substitution stuff, right? Keep it with the original X values. So I care not at all which method you use, but you got to just kind of keep them straight. I would encourage you to do this one. It technically is, well, it's a little bit less work. You don't have to like turn it into use and then rewrite it. You can just do it directly. But so this this example, while it looks, I mean, it doesn't look terrible to start with, it ended up being a pretty hard problem. The main complication, to be honest, like when I look at that problem or think about putting that problem on some sort of assignment, it's this that's the main complication, that you have to kind of come up with a secondary substitution. That's what makes this one a hard problem. And now it is a little messy because of all the square root business, but it's fundamentally, it's the secondary substitution, that just picking the right U isn't enough. You also need to substitute for the remaining variable. So it does come up. You'll see a couple of them, and quite possible you see one. Again, I think this one is a little messy afterwards, to be honest, for like a test, but you could see something of this type moving forward, possible. Questions about that? You know, I made it sort of longer than it needed to be because I wanted to talk through kind of some options and some different thoughts as we go through it. You could certainly do it more efficiently. And, you know, the other thing, as I was mentioning, you know, I'm really, like, if I gave you this problem, I'm mostly interested in you being able to get to here, you know, this antiderivative stage. So a lot of times I will probably not ask you definite integrals. I mean, you will have to do some of them for sure, because I want to see that you can do them. But if you can find the antiderivatives, I feel pretty confident you're going to be able to do the evaluating if you need to. Okay. Any other questions? I scare you away from questions. It was not my intention. Okay. All right, that's good. So that's better. I'm glad you're just in good shape versus. And again, maybe go back and watch that if you need to kind of go through it. Let me look at that question about the take home number 3. Yes, number 3 is where you have the derivative of accumulation function, and that is always a fundamental theorem of calculus. That's the part 1. And then just, of course, watch out because you need to use the chain rule there. Those are the ones that are sort of easy, but the idea is hard. So I think most students, my guess, are just kind of trying to follow patterns with those, and that's fine. It's totally fine, but there is a deeper meaning there. I don't know quite when I grasped that, but it certainly wasn't my first time through the course or my first 2 or 3 times teaching it, right? I can do the problems, but the understanding of what it is still, at least for a long time, was still tough. So that's, again, that's probably new to calculus for probably most of you. I imagine most topics you've taken before, you've probably understood mostly, or felt like you did, of what you're doing. And I think when you bump into calculus, all of a sudden there's some ideas that like, I don't really, it's hard to hold all that idea or information in your head, and some of that does take time, and it will sort of click at random times. But again, those problems you can do, you can follow the patterns and be pretty successful. Okay. Well, I wanted to, yeah, that's fine. That was a really good question to go through. That was, I wanted to do a question like that already, so that was good. Let me show you another, I'm going to do another example here of this. Another example of substitution here. Okay, so this is a indefinite integral, but again, it wouldn't change the difficulty very much if it was a definite integral. Our goal in either case is to find the antiderivatives. So it's definitely not one that we have a function that looks directly like this, right? Somehow it's something else. And so we're going to have to use substitution here. Is that clear how I'm choosing that? Because that's a big part of this, is understanding kind of what we're trying to do. It's really hard to do it if you don't even know that that's what you should try to do, right? So that's the first step, is to be like, okay, if I see a definite or indefinite integral of something I don't know, I've got to either change it or do a substitution. There are times when sine and cosine could be simplified into something better, but you know, and this 1 plus cosine is kind of close to something we can change using the Pythagorean theorem, but it's not quite the same, right? Sine squared plus cosine squared is 1, but that doesn't allow us to substitute very easily for this. So, and as we said before, or I've said before, there's no hard and fast rules here. These are all guidelines to kind of help us. But it's possible, certainly if you just ran into some arbitrary function, that substitution wouldn't work, and you might have to do some other strategies. Okay, so, but at the moment, it's all we have. So the u here and the du, well, the u is what we have to pick, or we have to choose. That's the crux of the problem, right? It's picking the right u. And there are a couple kind of reasonable options or reasonable things to try. There's also finite things to try. There's only a couple possible options. So if you try something that doesn't work, that's fine. Just start over, try a different thing. So for instance, you may pick u to be 1 plus cosine squared. It's not an unreasonable choice by any means. It's in the problem. So if I pick that for my u, and then I take du, you might then start to, you got to take the proper du, right? Remember, it's a chain rule. So 2 cosine x times sine x. And at this point, you might all of a sudden start to think, maybe, oh, maybe this isn't working out quite right? Because I have if this is my u, then sine x dx could be my du, but I also then have this extra 2 cosine of x, and I can't, I mean, it's possible I could solve for cosine and put that in for u. It's certainly not an obvious that this substitution is going to work. So, okay, let's try a different u. So this would be an example of choosing a little bit too much for my u, because the derivative then is a little too complicated. If I let u be cosine squared x, that is a little smaller, but it's not going to change the derivative or change the structure. So to really choose something smaller, I'm going to let u just be cosine of x. Then du is minus, I guess I forgot a negative in there. Sorry about that, right? Derivative of cosine squared is 2 cosine times minus sine. Doesn't change the issue. If I let u be cosine, then du is minus sine. And this all of a sudden, to me, feels better because I can see directly how to replace all the x's with u's. I need a negative in there. Right, so that's my strategy. I just put the constant in and multiply by the inverse of it on the outside. So the top then becomes du, and the bottom becomes 1 plus u squared. And this, hopefully, we recognize as the 1 over 1 plus u squared, which is arctangent. Because it's an indefinite integral, I have to put my plus c in. And because it's an indefinite integral, I have to replace the u with x. I don't have bounds, so I cannot switch all the way over to u's and never go back to the x's. I have to go back to the x's. There was a question in the chat about if the denominator is singular. So let's say this, well, this may be a bad example, but if the denominator is singular, like that, then yes, certainly I would almost always want to divide that denominator into those 2 pieces above, giving me hopefully a simpler pair of integrals to deal with. In this case, actually, it's a bad example. It's going to be the integral of cosecant, which is not one that we know exactly. Okay. But that is the right strategy. X that out. We'll pretend that never happened. Okay. Any other questions about integrals? Okay. Well, make sure you're finishing up the work from this section tonight, from these integral questions and that take-home work, and then look for that schedule and begin to get started on 6.1 for Thursday's class. It will be a big advantage if you started on that and made some progress. It will make our lecture much more productive on Thursday if you've struggled a little bit with the material. So I'll certainly respond to any questions that you have as best I can this evening. But try and get that done early if possible. And I will see you all hopefully on Thursday. Okay, so take care.
Thank you.
Thank
Yeah,
you.
you're welcome. Bye-bye. Thanks. Yep. Bye-bye.